recorded. Be aware. No. Okay, so a proof by Akiyama and Hwadal is, let me try to present the proof. Okay, so I'm guessing that most of you have seen Wissing's theorem, which says that if, so Wissing's theorem tells you that the minimum number, so chi prime g is the minimum number of colors one needs to color the edge set of the graph G such that no two edges which share a vertex get the same color. So if I have a graph, so I'm trying to color it, I will never color two edges like this, because that would mean these two edges share this vertex. I can't color them both red. Okay. So basically, in other words, if you are looking at any vertex, then all of its adjacent edges, all edges that come out of it, just like rainbow sticking out from a vertex. Wissing's theorem says that chi prime of G for any graph G is between delta of G and delta G plus 1. Here, delta is the maximum degree of the graph. Okay. Now, remember the graph we had was a cubic graph, which means that the maximum and the minimum degree, they are both 3. So it means that I can color it by at most 4 colors. So G is cubic, therefore chi prime of G is between 3 and 4. And that means let's take a coloring with 4 colors. Let's take an edge coloring of G with 4 colors. Okay, and let's say the colors are A, B, C, D. Okay, so let's say this edge coloring was so it was some mapping from the edge set of G to A, B, C, D, such that this property of that every time you had a vertex, all of its edges coming out of that vertex got distinct colors. Okay, let me just admit someone else. Or maybe they left already. Not sure. Okay, I admitted them. Okay. Now, given this coloring, I'm gonna use it as an auxiliary coloring, and then I'm gonna color my graph. So let me recolor the graph as follows. So let psi, or maybe let me call it C. C of E for every edge be as following. So I color it red if the color of the edge is either A or B. And I color it blue if the color of E is C or D. Okay, so it's like I'm interpreting this two as red, and I'm interpreting this two as blue. So what you can notice already after this coloring, so now our graph is colored red and blue. What can you say? What's the maximum degree of each monochromatic graph?
Cycles here, yes?
Yeah?
You have only problem with even cycles.
Yes, I might, yeah.
Component is just a simple pass. There is no problem here. It's just a linear forest.
Right. So because it was a proper edge coloring, I can say that let GR be the red graph and GB be the blue graph. So meaning that I'm only looking at the edges red or blue. Then first claim is that the maximum degree of both graphs is now at most 2. Right? Why is that so? Because so how would I have three red edges coming out of it, right? So to have 3 red edges from a vertex, I'm supposed, so this one has to be A or B, and this one has to be A or B. So let's suppose the first one is A, the second one, let's suppose it was B, and the third one, it has to be A or B, but I said that my original coloring was proper edge coloring. I wasn't allowed to have 2 A's here or 2 B's here, right? So I can only have at most, every vertex can see at most either 2 red edges or 2 blue edges. It might have 1, but it might have 2 of them. Okay. So, and what are the graphs whose maximum degrees at most 2? So this graphs is in the introduction, Petros said, they're either paths or cycles, right? So these graphs are going to look like either we are going to have, say like in blue, either I'm going to have cycles or I'm going to have paths. Well, same in red, right? So now what is the problem? So our whole goal was to do this coloring such that we don't see cycles like this. We only see paths. So now I'm gonna try to recolor it so that I break the cycle. Okay, so next goal is our goal to kill all monochromatic cycles. Are there any questions so far? Everything is clear? Okay, that's a good sign. Okay, so let's try to see how do we kill monochromatic cycles. Okay, so let's assume, let's take one cycle and recolor it. So what am I gonna do? So let me take, say, a red cycle. It has at least 3 vertices on it, right? So every cycle is at least a triangle. So let's say this is V1, V2, V3. Okay, now let's do the following. If I know, let's call this edge E1 and let's call this edge E2. Now, if E1 doesn't close a blue cycle, so what do I mean by this? If I don't have a path that goes like this, all blue, and the endpoints are V1 and V2, then if such a path does not exist, then, so this does not happen, doesn't happen, which means that I can actually recolor this edge to blue because I won't have a problem. I won't create a new cycle. So something like this does not exist. So, which means that we can recolor E1 to blue. And what does it do? It kills this cycle. It makes it now non-monochromatic. So I no longer have monochromatic. This one cycle is dead. And I did not create a new cycle. However, the problem is that it's possible that this path here is all blue, right? It's possible that there is such a path all blue. In which case, if I color this blue, then I'm creating a new cycle. So I didn't solve my problem. However, note that if E1 does close a blue cycle, then E2 won't. Why is it? So imagine that indeed there is such a blue path going like this, sitting on E1. And now let's see, is it possible that E2 also has the same picture? Well, let me see how it's going to happen. So it can't come all the way here, right? Because if it's completely disjoint, this guy has degree 4. Okay, that's a problem. Every vertex in our graph had degree 3. Or this path has to go and at some point has to join this path, right? But what's going to happen then? Now I have a vertex here, which has degree 3 in blue. And we said that this was not possible. Our maximum degree in both colors, blue and red, was 2. Which means that I can't have both E1 and E2 being in such blue, like sitting on such a blue cycle. So in that case, I will recolor my edge E2 to blue. So if E1 does close a blue cycle, then E2 won't. Therefore, recolor E2 to blue. And you do this one by one for each monochromatic cycle, and you get rid of all of them. Is there a question how this recoloring worked? Okay, very good. Okay, so as you noticed here, I never said anything about the length of the cycles, right? I did, sorry, the length of the paths. So this gave us, this proof gave us coloring of cubic graph in 2 colors, red and blue, such that every monochromatic component is a linear forest, but I had no bound how long these paths are. They can be as long as they want. Okay, so the question is now, can we actually say that they should be short? Okay, so this is conjecture by Vermont and Fouquet and Habit and Perroche says the following, that this can be done such that every path is of length at most 5. Okay, so this was this problem, this conjecture was looked by, I think this was early, like in 90s. So Jackson and Wormald showed that, so this is in 1996, they showed that paths of length at most 18, and then Aldred and Wormald showed that one can do a bit better, 1998, and they got paths of length 9. And finally, Thomason proved this conjecture. The conjecture is true. So let me just restate it so that we have it one more time cited. It says that every cubic graph can be colored by red and blue, such that I should say the edge colored, right? So it's very important. The problem is different when you do vertex coloring, which I will also tell you a little bit about. So it can be edge colored by red and blue, such that every monochromatic component is a path of length at most 5. Okay. Now, well, that problem is solved, but there is a different problem, which was open when we start looking at it. And this is a conjecture, which is by Wormald, and I think he made it in 80s. Says the following. Okay, so up to now, we were just asking that every monochromatic is a component is a path. We didn't require these paths to be isomorphic to each other, or so the number of paths to be the same, and there will be there'll be mapping such that these paths like one-to-one mapping. So I never asked anything about isomorphism between the graphs of color red and blue. And that's what Wormald asks for. It says that the conjecture, every cubic graph on n vertices, such that n is 0 mod 4, so it's divisible by 4, can be can be edge colored by red and blue, such that the red and blue graph are isomorphic. Okay, and not only that, moreover, they are both linear forests. Oops. So far, we have seen that this part of the conjecture is true. We can color the edge set of the cubic graph such that we are getting 2 linear forests. However, we haven't yet done the isomorphic part. Okay, so that's the conjecture we look at. And prior to our work, this was proved for some class of graphs, some restricted class of graphs by Vermont, Fouquet, Habib, Perroche, and Wormald in 84, and then in 2009 by Fouquet, Tuiler, Van Herb, and Voidra. But in the next today's and in the next lecture, what I'm going to try to do is to convince that actually you can do this for n sufficiently large and when the graph is connected. So theorem, this is joined with, so it's Shoham, Letzter, Gal Kronenberg. Which one goes first? Kronenberg goes first. So Gal Kronenberg, she's a postdoc at Oxford. Shoham, Letzter, She is a professor at UCL, and Alexey Pokrovskiy, also at UCL. So it says the following, that Wormald's conjecture is true for connected graphs on sufficiently large number of vertices. When I say a sufficiently large number of vertices, it means that I can take, there exists some n0 such that starting from that n0, all the graphs which are connected and are on n, at least n0 many vertices, to satisfy the conjecture. Okay. Any questions?
Lena,
Okay.
what the condition about the number of vertices n must be multiplied, n must be Fourier type? Why? It is some counterexample, or
Well, if you think about it,
generally,
it's
what about tight examples? Case of 5 in general.
Right. So I think it's so if my graph is cubic,
Yes.
EG is how much? It's 3n/2, right? That's the number of edges. And I'm trying to divide it into two parts, which are isomorphic.
Oh, okay.
So, right, if my EG1 has to have a necessary condition, it's going to be that it's going to be EG over 2 number of edges, and so is EG2. So, right, which means that I need to be able to divide 3n/2 into 2.
Okay.
So this needs to be an integer. That's why I have to have n to be divisible by 4. Otherwise, the
and in conjecture, the 5. Is there some example with you decompose this graph into linear forest with at least each path has length at least 4 or something
right?
like?
So yes. So that's a very good question. So let me not do those examples, but if you look at cubic graphs, okay, on 6 vertices.
Okay.
So these are tight examples.
Any?
Yes.
Oh.
Tight examples of Thomason's conjecture. But it is actually true that we don't know what happens if you forbid this to just these small examples. So if I tell you that your graph has, I don't know, at least 7 vertices, then I don't know if this construction is tight or not. So that's open. No one knows. Right. So we don't know of any other tight examples. Okay.
Yes, thanks.
So now let me rephrase the theorem that we proved, and then I'm going to give you an approximate version of it, which is going to be easier to prove, and we'll try to do that, or at least see some sketch of it. So our theorem says that if G is cubic, connected, and is sufficiently large, then G can be colored by edge colored by red and blue, such that the following holds. If I look at the number of paths of length k in blue color, that's going to be equal to the number of paths of the same length in red color. Okay, I didn't do a great job here, so this should be B. Okay, for every k. Okay, so this is number of blue paths of length k, and this is the number of red paths of length k. So I just rephrased the theorem, because once I have this, then I can definitely make an isomorphism between red and blue graphs. So the approximate theorem, which will be the first step to prove our theorem, is the following. So I will not ask for the number of red paths of length k and the number of blue paths of length k to be exactly the same, but I will ask them to be close to each other. And then I will also ask that the longest monochromatic path is short. So let me write the theorem. So approximate theorem, meaning that it sort of does what we want, but it's not yet enough. So for all sufficiently large n, every cubic graph can be edge colored by red and blue, such that two conditions hold. The first one is, well, actually three conditions hold, is that first, every monochromatic component is a path. Second says that the longest monochromatic path is of length at most, so O of log n, so some constant times log n. And the third one says that if I look at the number of red paths of length k minus number of blue paths of length k, then this is at most some constant times n to the 2/3 for every k. Okay, so P1, P2, P3. So is it clear why I call this an approximate version? It's sort of does what I want. This part sort of does what I want, but it's still not enough, right? I want this to be 0, but right now I'm getting that they can be far from each other by at most c times n to the 2/3. My next step is going to be actually to get rid of this these errors. So I'm going to recolor my graph such that every time I get this deviation between the number of red paths and the number of blue paths from possible n to the 2/3 to 0. Okay. But this is the first step for our proof. Okay. Any questions? Another thing you can notice that I did not ask the graph to be connected here. So for an approximate result, I actually do not need the connectivity. Just Okay, so let me start with the proof, or rather proof sketch of the approximate theorem. Okay, here's how it goes. So let's first color our graph by Thomasson's result, by say color EFG by let's say green and purple. Okay, such that what did we know? That every monochromatic component is a path of length at most 5. And now, so now I have this path, right? Like I have a red or green, green or purple. And let's suppose I have a purple path. What I'm gonna do, I'm gonna toss a coin, and with probability 1/2, I'm gonna color this like the following. So red, first blue and then red, then blue, and then red. Or I'm gonna do the opposite. So the first edge is gonna be red, and then it's gonna be blue, and then red, and then blue. And I do this for every monochromatic path. So the same for any length, right? I don't really care that the length here is 4. The main point is that with probability 1/2, I start with the blue edge, and then I alternate. With the probability 1/2, I start with the red edge, and then alternate. So that's my first step. So, now, after this coloring, so you might be like thinking, okay, maybe that is enough. Maybe this recoloring would be enough to already get what we want. Well, in certain ways, yes, in other ways, no. So first thing you notice is, what can you say if you look at let's look again at the red graph and the blue graph. What can you say about the maximum degree of the red graph and the blue graph after this? So can I have a vertex of degree 3 in red? Well, what would it mean? It would mean that, right? So it's so if I have like, what do I want to say? So if I'm looking at my original coloring, then so I either had purple, so it was some path, and then green, or I had maybe green, and purple, right? So this is the two pictures I can see in the after Thomasson's coloring. So either there is like a path of length at least 2 that passes through this vertex, and this green one is just a, it starts here, right? It maybe goes green afterwards, but it starts here. Or there is a path of length at least 2 passing through this vertex V, and then it becomes purple. So if I color it with this procedure, right, what am I gonna see? So at least I'm gonna see at least 2 edges of distinct colors, because let's assume that this purple path got colored like this, red and blue. I don't actually care about the order. And maybe this green one is red, or maybe it's blue, but no matter what it is, I know that at the vertex V does not have blue degree tree or a red degree tree. It's the same in the other direction, right? So if I look at this picture, this green path is going to be either a red blue or blue red. I don't care about the order at the moment. What I care is that I will see at least a picture like this. So from V, I will already have red and blue color sticking out. And the purple, maybe it's red, maybe it's blue. But no matter what it is, it says to me that such pictures cannot happen, right? So after recoloring, again, I can say that the maximum degree of both red and the blue graphs is at most 2. Questions? Does this make sense? Okay, good. So again, we're kind of in a good shape. We can say, okay, well, that is nice. We only have to worry about paths and cycles. And maybe I could hope that this recoloring would eliminate long monochromatic paths. But that is not going to be true, right? Say that this coloring won't eliminate the possibility of long monochromatic paths. By the way, just a question, when shall I stop today? I just see lots of people leaving, so I'm wondering if I'm already over time.
Let's see. More or less, if you can come up with some logical point to stop.
Okay, so I will just show that this recoloring is not eliminating long monochromatic paths, and then during the next lecture we'll see how to fix that and how to continue. So, okay, so suppose after recoloring, let's imagine we had like a long path of some color. Let's assume it's a blue. So possibly I see like a path. And here when I say long, it can be even of length, like of order n. So all I know is that, okay, how did this guy end up being blue? Because there was some purple path, right, sitting here, and maybe this, when I flipped the coin, the first edge became blue and the second one became red and so on, okay. And then the next one, it's blue. So, okay, so maybe it must have been coming from some green path, okay. And again, maybe it was a long path, maybe it was a path of length 1. And then this was another path and so on. So I'm trying to say that all these blue edges come from certain blue or red paths which look like this. So these vertices for me are identical. That's what I'm imagining, okay? And these guys are going out. So each one of these blue edges comes from some potentially some red, some purple or green path. Okay, something like this. I wasn't paying attention of, so it can be anything. But the point is that, okay, so what's the possibility that I actually ended up with this specific coloring, meaning that I ended up flipping this coin such that this guy became exactly blue and this one became red, this one became blue and so on. Well, so of course, some of these events are not necessarily independent, right? Like it's possible that maybe I will have, let's say, I'll have like, I mean, it's possible that some of these paths, not many of them, they are short, but some of these paths can have, can be the same, right? So this might be the same path. So which means that the event of this edge being blue and this edge being blue is not independent because they both came from the flipping the same path. However, all of our paths were short, they were of length at most 5, which means that if I have such a long path, I will be able to collect a large proportion of blue edges whose events were independent. So given a monochromatic path P of length, let's say some constant times n, there exists a collection of edges in P whose events or corresponding events. And the event is that the path that this blue edge is coming from, in this case it was this, they are independent. Okay, and I really should say that, okay, there is a collection of edges, maybe Cn over 100. So I don't want to lose too many of such edges. So it's still linear proportion of edges who are independent. Well, then the probability that my path P is monochromatic, right? It's if I want to just give some loose bound, then it's at most the probability that this independent set of edges are all monochromatic, and the probability of that was what? Each one was, the path was either being colored blue, red, or red, blue. So I'm saying that exactly the order that I want it happened. So it's like 1/2 to the Cn over 100, right? But now this is huge because I can't take a union bound. We can't take union bound on the number over all possible monochromatic paths. That's because there are too many of them. So to imagine why there are too many of them, so imagine, so this is my blue path. How many such blue paths are possible, or red paths? At every vertex, right, I have either a choice of going via the purple or via the red. So it's roughly gonna be 2 to the n. So it's too big because the number of such paths is too large. Of order 2 to the n. So if I multiply those two numbers, I'm really going to be in a bad shape. So the union bound won't work. So this won't work. And what we'll do now is, well, not now, in the next lecture, we'll see how to fix this, right? So we'll see that, I mean, it's not really 2 to the n, it's 2 to the Cn. So whatever the length I started with, because at every point, right, if I'm looking at a thing of length Cn, then I'm going, at every point, I have two options, either follow the green path or the purple path. So the number of these guys will be of order 2 to the Cn, and this is not going to be able to kill this. You can try other methods, but you will not be able to say that, okay, I can eliminate all long paths. So next time, we will continue recoloring And what will that mean is that we'll break or kill all cycles, monochromatic cycles, and long paths. So how do we avoid having long paths, and how do we get rid of monochromatic cycles? Okay, I think that's all for today. Seems like that's a good place to stop. Questions?
Թվում ամենահետաքրքիրը մնաց մյուս բանի վրա։
Yeah, that's a warm-up page. I'll send my lecture notes to maybe Armen, and it might be helpful for students to have a look at them before next, next lecture. Just it will be slightly more technical, the next one, so it would be good to have a look at it. Any questions?
I think in the next lecture, when it comes more to the proof part, some questions more interesting could appear. This was like the teasing part, so I'm looking forward to it.
Okay, that's good.
So I think a good introduction, but the most important parts will be next time, I think.
I also was a great introduction, but I think next Saturday I'll work, so I can't participate. Would we record it again?
I believe so, yes, we'll record it.
Thank you very much.
And just one
Քեզել Անուշ ջան, կներես email-ից չեմ պատասխանել, նոր հիշեցի։
Եմ կսպանեմ։ Bye bye.
Bye Անուշ ջան։
Լիամնա, մի հատ ուղակի նոթ էլի, չգիտեմ, իմ մոտ դրա հետ կապված ինչ-որ խնդիրներ էին ժամանակին առաջացել։ Ինչքան գիտեմ, այդ երբ որ գագաթներն ես տրոհում, դա կոչվում է partitioning, երբ որ կողերն ես տրոհում, դա decomposition է, եթե չեմ սխալվում, էլի, դեռ տարբերություն կա այդ տերմինների, էլի։
I don't know, I have seen both. Some people say edge decomposition, some people say edge partitioning. Okay. I feel like in the recent papers, it's more common to call it decomposition. But if you look at the older papers, like 80s, 70s, I think they do say edge partition. So I'm kind of using both, but you're right. Probably I should be more.
Because when I read the title, I expect it will be about partition of vertices, something like this, but then edge coloring. So, okay.
I will show you some results and conjectures also on the vertex coloring. So you can ask the same question, exactly the same question, but for vertices, you want to color the vertices red and blue. And there are known results there too. So.
But is it something about our regular graphs, not cubic? Because
there is a conjecture. So
R/2, something like this, it will be, yes.
So there are two things. One is you have cubic graphs and you would like to red and blue color it such that there are two types you can go for. One is that the monochromatic components are isomorphic, and this is solved by Benny Sudakov, Alexey, Pokrovskiy, and Shagnik Das in the sense that it's proved for all n sufficiently large and connected graphs. This was Ando's conjecture from 90s. There is a different conjecture which says what the monochromatic monochromatic component should be, and that's open. The conjecture says that they should be actually matchings, and this is open, and I think it's hard. Well, for certain graphs, I think the graph should be bridgeless, so two connected.
Oh, yes.
And then there is a conjecture that you are mentioning. So if you have k regular graphs and now you want to do the same thing there, how many colors you need? So I think the conjecture says if you have 2k plus 1 regular graph, you can k color it such that all monochromatic components are again linear forests, and that conjecture is open. And I think it's hard.
It's a Ferrari conjecture. Something.
Yeah, I think so. I'm not sure whose conjecture is it. To me, I could never track down whose conjecture was this. But maybe it's so old that it's like now it's just folklore. But it's hard, I think.
There is also a big difference in complexity because, as I know, just simple arboricity is a polynomial problem, but linear arboricity is NP completed. I know.
Yeah, I see. Yeah, I haven't. So it's interesting that you mentioned because I learned this conjecture from Alexey's talk when he presented their result on the vertex coloring, and I knew it about like that it's Wormald's conjecture on the edge coloring, but I didn't know that this is known in the literature as arboricity until very recently when I started writing the paper, and suddenly all these papers came out and they were all calling it arboricity. Yeah. So
okay.
Maybe I stop recording.